Good morning, everyone. So welcome to my YouTube channel, Math Satram. So today we are going to see 27th lecture on demand and demand. Okay, so let us start today's session now. So today we'll study intermediate value property. Okay. So what is intermediate value property? Let F closed interval AB to R be a function. Be a function. Then F is said to have intermediate value property if given if lambda belongs to R with lambda in between FA and FB, then there exists C belongs to closed interval, C belongs to open interval AB such that FC is equal to lambda. Okay. FC is equal to lambda. Okay. Note that intermediate value property is called IVP in short. Okay. In short, intermediate value property is called IVP in short. Okay. So remark, every continuous function f closed interval AB to R has IVP. Okay. Second, A non-continuous function also may have IVP. For example, I am giving example. You can see this by example. We know that continuous function has IVP, but non-continuous function also may have IVP. For example, I am taking this function. I am taking f close interval 0 to r defined by fx is equal to, it is 1 if I am taking x in this range. Okay. Okay. And this is theory minus x if we are taking x in this range. Okay. So this function is continuous at this function. What is the graph of this function? The graph of this function is zero is here, 1 is here, and 2 is here, and up to 1, less than 1, it is actually 1. Okay, 1 up to this, and this is open here. Okay, after that it is a line. Okay, it is a line. From this to this to this. This is line. Okay. So this actually, what is the range of this? What is the range of this? What is the range of f? It is nothing but closed interval 1 to 2. Okay. But my function from interval 1 to 2 cover this range. Actually, this range is also covered by the image of interval 1 to 2. Okay. 1 to 2. Okay. So by continuity, this part can be covered. Okay. So any value in between 1 and 2 can be covered by continuity of this function f on the closed interval 1 to 2. Even this function is not continuous at 1. F is not continuous at x is equal to 1. Okay. So if they are taking any value, so take lambda belongs to R such that f lambda lie in between f0 and f. What is f1? F1 is nothing but 1. And what is lambda? Lambda is in between f images f0 and 2. So what is f2? F2 is actually okay. Okay. So now you see that one thing I should write here. I should write here. I should change the map little bit. Okay. So I am taking the function 1 to 2. I am taking this function. One to 2. I can add one more function in this. What is that? To take this one. You can take this function x. If you can take this function x1 plus this is -1, the -1, x -1. If we are taking x in this range, okay. So what is the graph of this here? This is actually this at 3, okay, at 3. Now I am going to change the interval, okay. So I am taking change the interval. So this is defined on this. Now this function is not continuous at x is equal to 1. Okay. So I am writing what is this? The range is 1 to 4. Okay. One to 3 you can write. Okay. This function is not continuous. This function is not continuous at x is equal to 1. Okay. Now take any lambda. Take lambda belongs to R such that F0 lambda F3. So what is this? This is 1 and this is lambda. And what is this? This is 2. Okay. Okay. This is now, but function is continuous. But this is nothing but F. This is nothing but F. F1. Okay. And this is nothing but F3. Or you can write F2. But on the interval. It is F2. Okay. So 0 to 3. It is 0 to 3 is 1 to, and this is actually 2 to 3. Okay, no problem. 2 to 3. You check 2 to 3 is actually the range 1 to 2. Okay, so this is F2 actually. Okay, F2. This is F2. F. Okay. So this implies F lambda F. But function is continuous on the interval 0, close interval 0, 3. F is continuous on close interval 2, 3. So imply, but every continuous function has an intermediate, but continuous function has IVP, implies there exists C belongs to R, C in this range such that FC is equal to lambda. Therefore, there exists C belongs to R in between such that FC is equal to lambda. So a non-continuous function may have IVP. Okay. Now my question is that suppose, note that remark, I am writing remark. Suppose you have it. Suppose f x is equal to c constant function on closed interval a b. Okay. Okay. Then there does not exist. So you take there does not exist any lambda belongs to R such that F A F B. Why? Because both are C. Because function is constant, which is not possible. There does not exist any lambda because function is constant, and any lambda will not exist in this range because both the values are C. A value cannot be greater than C and same value cannot be less than C. Okay. So it means IVP is automatically satisfied because we do not have any lambda. So IVP is automatically satisfied. This implies IVP is trivially satisfied because we do not have any lambda belongs to R lambda in this range to check IVP. If you do not have any lambda, what you will check? So IVP is trivially satisfied. Okay. Okay. That is why in definition we are writing lambda should be still greater than FA and still less than FB. Okay. That is why this is the definition. Okay. Because if you cannot find any lambda, such lambda, for those functions, IVP is trivially satisfied. Okay. Okay. Now, I'm writing a theorem. Let F close interval AB to R, AB to R, be a differentiable function such that f dash A into f dash B is less than 0. Okay. Then there exists C belongs to open interval AB such that derivative of f at C always vanishes. Let's see its proof. Okay. Since f dash A into f dash B is equal to is still less than 0, we get that either, because their product is negative, it means both the f dash A and f dash B have negative signs. Okay. So either f dash A is negative and f dash B is positive, or f dash A is positive and f dash B is negative. Otherwise, their product cannot be negative. Okay. They cannot be of same sign. So, without loss of generality, we assume that first case f dash A is less than 0 and f dash B is greater than 0. Because we will do the proof for this case, the same proof can be repeated for this case, f dash A is greater than 0 and f dash B less than 0. So without loss of generality, we are assuming that f dash A less than 0 and f dash B greater than 0. Okay. Okay. Now, f close interval A, B to R is continuous function because it is differentiable. Differential function is always continuous. So, okay, because f is differentiable on AB, so it is continuous. Okay. Okay. So every continuous function attains its bounds. So there exists okay, x1 and x2 belongs to closed interval AB such that f1 is nothing but supremum of fx on this interval. Okay. Because continuous function attain its supremum and infimum. Okay. And f infimum of fx x belongs to closed interval AB. Okay. Okay. we claim that that x1 and x2 lies in between A and B. Okay. X1 and x2 lie in between A and B. Okay. Why? Firstly, you know that F is infimum. F is infimum. So it will be less than okay. So x1 and x2 lie in between A and B. Okay. 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 So now what is the now observe that f dash x1. What is this? F dash x1 is equal to limit h tends to 0 f x1's h minus f now you take x2 here. X2 here. So this is x2 minus f x2 upon h. Okay. So but so this will be the inside quantity is non-negative. Why? Because infimum attain at 2. Infimum attain at x2. So every value will be great. So this value x2 plus h is another point on closed interval AB. So it will be greater than or equal to, because fx2 plus h is greater than fx2, because this is infimum. x2 point is infimum, point of infimum. So this quantity is non-negative. Inside thing is non-negative. Okay. So its limit will be also non-negative. So this implies f2 f dash x2 is non-negative. So now this implies x2 cannot be equal to A, because if x2 is equal to A, then f dash x2 will be f dash A and fx2 is and this is then, but f dash is less than 0, which will be contradiction, which will be a contradiction. So that is why x2 cannot be equal to a. Okay, that is why x2 cannot be equal to a. Okay, x2 cannot be equal to a. So x2 cannot be equal to a. Now this is the right hand limit. Similarly, we calculate the right hand limit here. Clearly, from the right hand limit, so calculating it by right hand limit, as is positive. Okay, that is why this is happening. Now, if I consider the same thing, considering the same thing, f dash x2 can also because function is differentiable. I take right hand derivative or left hand derivative. The value of derivative x2 will be, you will get the derivative at x2. Okay. So now considering left hand limit, f x2 plus h minus f x2 upon h. But here I can take minus in common. I can take minus common. It will be h dash 0 f x2 plus h minus f x2 upon h minus h. Now this quantity is positive. Now this quantity is positive. Inside numerator is also positive. Okay. So what we got? Inside thing this thing is positive. But this sign is negative here. This sign is negative here. So that is why the limit will be, resultant limit will be this. This implies f dash at x2 is less than equal to 0. Okay. So now, so this implies x2 cannot be equal to b, because if x2 is equal to b, then f x2 is equal to f dash will be there, but it is strictly greater. Okay, which is a contradiction. Okay, therefore x2 cannot be equal to it. Okay, so what we conclude? Neither x2 is equal to a, neither x2 is equal to b. So let's say this question 1. So let's say this equation. So finally, we have that x2 will lie in between, because x2 is neither a, x2 is neither b, and x2 belongs to this interval. So we get x2 lies in between this. Okay, from 1 and 2, we have, from 1 and 2, we have From 1 and 2, we have what we have. From 1 and 2, what we have. From 1, what we have. F dash x2 is greater than equal to 0. And f dash at from equation 2, we have less than equal to. So combining, what we get. Combining, we have what we have, because derivative is at x2 greater than equal to, and derivative at same point is less than equal to 0. So what you can conclude? Okay, f dash at x2 is equal to 0. Okay. Similarly, you can show. Similarly, we can show that x1 is also in this range and f dash at x1 is also 0. Okay. So we can take put or you take C is equal to x1 or x2. You can take C1, either x1 or x2. Therefore, then there exists C belongs to R, which is in this range, such that f dash at C is equal to 0. Now we are doing, so theorem is proved. Now we are doing one corollary. Let f close interval a b to R be a differentiable function then f dash has IVP on close interval a b. Let's see its proof. Okay, let's see its proof. Let lambda belongs to R such that f dash is less than lambda is still less than f dash b. Okay. Now put gx is equal to, okay, f x minus lambda. Okay. Then g close interval a b to R is a differentiable function Okay. It's a differentiable function. Okay. Now check that g dash x is, what is this? F dash x. So you take the function gx is equal to fx minus lambda x. Sorry, you take x here. Take here. Okay. Now g is differentiable function. What is the derivative of this function? Minus lambda. Okay. Now what is this implies? What is g dash at a? What is this? F dash at a minus lambda. But this is still less than 0 from this, because we know that f dash a is still less than lambda from here. So their difference f dash a minus lambda will be still less than 0. And Similarly, what we have G dash at B, what is this? This is F dash B minus lambda. So what will be this? This will be greater than 0. Okay. So what we have? We have G dash A is less than 0 and G dash B is greater than 0. So this implies G dash A into G dash B is less than 0. Product is less than 0, is less than 0. Now by theorem, there exists C belongs to R, C in this interval we have C belongs to R, C belongs to R, C in this range such that F dash at, G dash at C, G dash C is equal to 0. But what is this? This is F dash C minus lambda is equal to 0. Okay. So what we got? This implies F dash at C is equal to lambda. Okay. So this implies, therefore, given any lambda belongs to R, given any lambda belongs to R, any lambda belongs to R, please, F dash A, F dash B, we have C belongs to open interval A, B, such that F dash C is equal to lambda, C is equal to lambda, C is equal to lambda. Hence, F dash has IVP. Hence, F dash has IVP. Okay. IVP. Okay. Now another corollary. Another corollary. Another corollary is let F G belongs to, sorry, F is Riemann integrable. Okay. And phi closed interval A B to R be a differentiable function such that phi dash x is not equal to 0 for all x belongs to closed interval a b. Okay. Then a to b f x phi sorry I made a mistake. The differentiable function so this is alpha and beta here. Alpha beta ये differentiable function such that a is equal to phi alpha, b is equal to phi beta, and phi dash y is not equal to 0 for all y belongs to closed interval alpha beta. Then a to b fx dx is equal to alpha to beta f composed phi y phi dash y d1. Okay, let's prove it. Okay, so now phi dash y is not equal to 0 for all y belongs to closed interval alpha beta. Okay, we claim that either phi dash y is greater than 0 for all y belongs to alpha beta, or phi dash y is still less than 0 for all y belongs to alpha beta. Okay, so we will prove it by contradiction. If possible, suppose that there exists x1 x2 belongs to closed interval alpha beta such that x1 less than x2 and phi dash y, because we are assuming that there exist 2 points at which it is positive and another point it is negative. It means this point y1 into y2 is non-negative. Okay. So write here y1. Okay. y1, y2. Okay. So that y1 is greater than y2. So that this is happening. Okay. It means at one point it is positive and another point it is negative, or at one point it is negative and another point it is positive. Okay. Then by theorem, there exists T. There exists T. C will be lies in between such that phi dash at C will be 0, which is a contradiction. Okay? Contradiction to the fact, which is contradiction to the fact that phi dash derivative of phi is never 0 on closed interval alpha beta. Okay. So that is why this is not happening. So therefore phi dash y is greater for all y belongs to alpha beta, or phi dash y less than 0 for all y belongs to alpha beta. Okay. So what is the meaning of this? We know that if derivative is positive, then function is monotonically phi. If derivative is strictly positive, then function is phi is strictly increasing. Strictly monotonically increasing. The meaning of derivative is greater than 0, strictly monotonically increasing function. Now, if derivative is negative, what is the meaning of this? The function is monotonically decreasing, strictly monotonically decreasing. So what is the meaning of this? The meaning of this is phi is strictly monotonically. What is the meaning of this one? This much. The meaning is this: phi is strictly monotonically decreasing. We know that any of the following case, either it is derivative is positive or derivative negative, again holds. It means either the case phi is monotonically increasing or monotonically increasing strictly follows. So any of the following cases holds. So what is the meaning of this? This implies that combining both the facts, what we have that phi is strictly monotonic function. Phi is strictly monotonic function. Now by change of variable in integration, I have given a lecture on this. You see lecture. You see You see, Riemann integration lecture 26. See, Riemann integration lecture 26. We get what we get, because I know that phi is strictly monotonic. We know that if f is Riemann integrable, phi is strictly monotonic function, and we know that phi is continuous because h is differentiable. So we get what we have. We get because function is a to b fx dx is equal to alpha to beta f composed phi y phi dash y dy. Why this is happening? This is happening of lecture 26, change of variable theorem. Okay, because function here f is Riemann integrable. F is Riemann integrable. So so phi also Riemann integrable. Okay, phi is Riemann integrable. Okay, phi is Riemann integrable because phi is continuous. Differentiability implies continuity. Okay, that is why this is Riemann integrable. And what is alpha? Alpha A is nothing but phi alpha. Okay, and B is nothing but phi beta. B is nothing but phi beta. Okay, and phi is monotonic, and phi is strictly monotonic. Is strictly monotonic. That is why this is happening. We can use change of variable here. So that is why this is happening. So finally, I am writing it again. Formula. Writing this. So this implies a to b fx dx is equal to alpha to beta f composed phi y phi dash y dy. Okay. So this is done now. This is done. Okay. So it is proved. So this is for understanding purpose only. The right, on the right I have written something that is for understanding purpose. Okay. I am writing another corollary. Let f close is Riemann integrable over closed interval AB. Okay. And phi closed interval alpha to beta are be a differentiable function such that A is equal to phi alpha, B is equal to phi beta, and derivative of phi has finitely many zeros on interval alpha beta. Then A to B fx dx is equal to alpha to beta f composed phi y phi dash y dy. Okay. Proof. Now phi dash has finitely many zeros. Let's say these zeros are these zeros are beta 1, beta 2 up to beta n. Okay. It means f beta I is equal to 0 or I goes to 1, 2 up to n. Okay. Consider the subintervals. Consider the subintervals alpha beta 1. Okay. Beta 1, beta 2 and so on, beta minus 1, beta n, and last interval is beta n beta. Now on this interval, because on this interval f is on this interval, because on this interval function will not vanish. So on this interval function is not vanishing. Function is not 0. Similarly here function is not 0 because whatever 0, it has only finite number of zeros. We have identified the 0, that is beta 1, beta 2, beta n. So here function is not 0. Not 0. Okay. So by previous corollary, we have what we have on this interval. What we have alpha to beta 1 fx dx is equal to what we have a to phi beta 1 by this corollary alpha to beta 1 f composed phi y. Okay. Phi dash y dy. Why I am writing phi beta 1? Because in this interval function is non-negative. So it is mostly monotonically increasing or decreasing on the base intervals. Is every function which is 1, 1, 1, 2 strictly every function which is differentiable, it means continuous, and strictly increasing or decreasing, such functions are invertible. Okay. So if you have a strictly increasing function, it means that is 1, 1. Okay. And because here it is onto also, that is invertible. And invertible, we can take its inverse, because such functions are invertible functions. Okay. We have done we have discussed it in previous lecture, 26th lecture. So that is why I can write this. Okay. Similarly, I can write phi beta I to phi beta I plus 1. Okay. Fx dx is equal to beta I to beta I plus 1 f compose phi y phi dash y dy. Okay. And final interval. So this is I varies from 4 I from 1 to up to n minus. Okay. And final is phi beta n, and this is b. Fx dx is equal to beta n to beta is equal to f compose phi y phi dash y dy. Next, what is this? A to b fx dx interval can be taken as this one, phi beta 1 fx dx, and this can be written as summation I goes to 1 to n minus 1 phi beta I to phi beta I plus 1 fx dx, plus last one is phi beta n to b fx dx. Okay. Now, but this is equal to what? This is equal to this is alpha to beta 1 f composed phi dash y dy plus summation I goes to 1 to n integration beta I to beta I plus 1 f composed phi y phi dash y dy plus beta n to beta f composed phi y phi dash y dy. After so what is this? This you are adding intervals in subparts. So what will be this then finally? This is equal to alpha to beta f composed phi y phi dash y. So finally what we got actually? We got this one. A to B, okay, fx dx is equal to alpha to beta f composed phi y 5 dash y dy. Okay. So this is proof. So in this lecture, what we have we have studied intermediate value property, and we have shown that that derivative function has the derivative of the function has IVP, intermediate value property. Using that, we have shown that derivative of phi is non-negative. In change of variable, phi turns out to be still a monotonic function, and we can use change of variable theorem here. Okay. And if a derivative of phi has finite number of zeros, then still we can use change of variable function. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much. We will see you in next lecture.